All right, ready to dive into some physics? We've got a whole stack of notes here all about motion. Honestly, just skimming through kind of makes my head spin,
I hear you. It can be a lot to take in.
but that's why we do these deep dives, right?
Right.
Got to break it all down, figure out what's really important.
Absolutely. And, it's funny how much we just take motion for granted.
Yeah.
It's everywhere, and
Yeah.
I mean, everywhere we walk, cars drive, planets are out there zipping around stars.
True.
But then you dig into the physics of it all, and it's surprisingly complex.
Well, before we get lost in space, maybe we should start with the basics.
Sure.
What is motion?
Mm-hmm.
Like, I think I know, but then I see stuff about point objects,
Uh-huh.
and I'm like, wait a minute, what?
Yeah, we got to be precise, when we talk physics. So motion, at its heart, it's simple, just a change in position over time.
Right.
As for point objects, that's a way physicists simplify things. Think of it like this. You want to track a car driving across town. Instead of worrying about the car's shape, all the little details, you focus on one point, usually the center of mass, and you track how that point moves.
So we're like shrinking the car down to a tiny dot.
Yeah.
Doesn't that seem oversimplified, though?
It can be. That's why it's important to know when that simplification works and when it doesn't. So if we just want to see the car's general movement, like over a long distance, the point object thing, that's fine. But if we're analyzing a crash, where the car's spinning and rotating, then things get more complicated. We got to factor in more details.
Makes sense. But center of mass, that sounds kind of technical.
It's really just the balancing point.
Oh, great.
Like if you could perfectly balance the whole car on a pin, that point would be the center of mass. All the car's mass is concentrated there.
So if I was trying to balance a ruler on my finger,
Yep.
the center of mass would be right in the middle.
Exactly. And we'll see, as we talk about more types of motion, how important that center of mass is. But to make this deep dive a little easier to handle, we're going to focus on a simple type of motion, movement in a straight line. Physicists call that rectilinear motion.
No loop-to-loops or anything.
Not for now. Straight lines are the foundation. Once we nail those down, we can start adding in curves and turns.
Sounds good. So how about how fast things move along those straight lines?
Speed. Always a fun topic.
I'm seeing instantaneous velocity in these notes, and I'm getting some physics flashbacks. Not all of them good.
Instantaneous velocity is a cool idea, though, once you get your head around it. See, we talk about speed in general, like saying a car was going 60 miles an hour,
Right.
but that's just an average speed, right? Over a period of time.
Yeah, because the car wasn't going 60 the whole time. Probably sped up, slowed down.
Exactly. Instantaneous velocity is all about a specific moment. It's like looking at your speedometer right now and seeing 45 miles per hour. And the wild part is, this idea, it connects directly to calculus.
Calculus. Like derivatives and all that.
Yeah.
I thought we were trying to keep things simple here.
Don't worry, we're not diving deep into calculus, but it shows how these basic ideas, like velocity, are tied to some heavy math. In a nutshell, calculus helps you find the rate of change of something. And velocity, it's the rate of change of position.
So if I had a graph showing a car's position over time, calculus would let me figure out the car's speed at any point on that graph.
You got it. What's cool is we can actually see this without even doing the math. You can draw a line that just touches the graph at one point. It's called a tangent line. And the slope of that line tells you the instantaneous velocity right there.
Okay, I think I get the general idea. Even if the math is a little fuzzy, so even when something's moving in a straight line, its velocity can be changing all the time.
All the time. And that brings us to acceleration. Yeah, and this is where it gets interesting. Most people, when they hear acceleration, they think speeding up. But physicists, we think about it a little differently.
Okay, so what else could it be? Like hitting the gas and turning the steering wheel at the same time.
Well, turning brings in other stuff, other physics. But for now, let's stick with straight lines. Even then, acceleration is about any change in velocity.
So speeding up, that's acceleration, I get it.
Right.
But slowing down too.
Slowing down is acceleration too.
Wouldn't that be like deceleration?
You're right. That's what we say normally. But in physics, it's all acceleration. Slowing down, that just means you have negative acceleration. Velocity is going down.
Okay, I'm starting to see how physicists think.
Good.
But hold on. These notes say acceleration can happen even when your speed stays the same. How's that possible?
Remember, velocity is not just speed, it's speed and direction. So imagine a car going around a circular track, perfect circle, and it's going at a steady speed, speedometer doesn't move, but it's constantly changing direction. And velocity includes direction. So if direction changes, velocity changes, which means acceleration.
Whoa, okay. So even going in a circle at the same speed, you're still accelerating. That's kind of weird, but I guess it makes sense.
It all comes back to that definition of velocity. And just like velocity, acceleration has both magnitude and direction. Magnitude tells you how much velocity is changing. Direction tells you, well, which way it's changing.
This is making me think of Galileo and falling objects. Didn't he figure out that stuff about gravity and acceleration?
You're on the right track. Galileo, he was a rock star, when it comes to motion anyway. He was the first to really understand that objects in free fall, they experience constant acceleration.
Because of gravity.
Exactly. So even though we think of falling as just straight down, it's actually accelerating downwards at a steady rate.
And that rate's about 9.8 meters per second squared.
Yep. Every second an object falls, its downward velocity increases by that much, 9.8 meters per second.
Oh, physics class flashbacks. I see some figures in these notes, too.
Yeah.
2.2 and 2.3, I think they're graphs.
Right. Yeah.
Showing how position and velocity change over time with different kinds of acceleration.
Graphs are awesome, aren't they? Super useful for getting a picture of what's happening. So much information packed into a simple graph. For example, imagine an object accelerating at a steady rate.
Okay.
Its position time graph. That would be a curve. But the velocity time graph, that'd be a straight line.
Wow. Okay. Can't put it off any longer. Got to talk about those equations. There's some serious math here.
Yeah, equations can seem scary, but think of them as tools. They connect all those quantities we keep talking about. Initial velocity, final velocity, acceleration, time, displacement. It's all linked together.
So with those equations, could you predict like how long it would take a rocket to get to a certain speed?
You could.
Or how far a baseball travels when it's hit?
That's the cool thing about physics. You can quantify and predict. And those equations are like a secret code to unlock the mysteries of motion.
All right, feeling a little better about the equations now. But we got to talk about Galileo's odd numbers. These keep popping up in the notes.
Oh, this is a good one. It all goes back to free fall. Motion just under the influence of gravity.
Like dropping a bowling ball in a vacuum chamber.
Exactly. No air resistance to mess things up. And Galileo noticed something about the distances an object falls in equal time intervals. They're in the ratio of odd numbers.
Odd numbers.
Yeah, 1 to 3 to 5 to 7 and so on.
Wait, so if it falls like 1 meter in the first second, then it falls 3 meters the next second, then 5 meters the next, what's up with that?
It seems random, I know. But it all comes down to that constant acceleration from gravity. The object's velocity keeps increasing at a steady rate as it falls. So in each second, it's falling faster than the second before. That's why it covers more distance each time.
Okay, my brain's working on that one.
Some things take a bit to really sink in. It's all good. But while you're thinking about that, how about we bring things down to earth? Literally, let's talk real-world stuff.
Real-world stuff. Huh? So we've been shrinking cars down to points.
We have.
And figuring out Galileo's weird number patterns. I'm feeling pretty good about all this motion stuff.
Me too.
But you said down to earth. Literally. Like how this all applies to everyday life.
Yeah, exactly. All this stuff we've been talking about, it's not just theoretical. It's got real practical uses. Think about driving, for example.
Okay. But how do falling bowling balls connect to driving?
Not directly, no. But remember, those equations, the ones that link velocity and acceleration and all that, those same equations can help us understand things like stopping distances and reaction times.
Important for safe driving, yeah.
Very important.
So stopping distance is like how far your car goes after you hit the brakes.
Yeah.
Before it actually stops.
That's it. But it's not just about your brakes. Stopping distance is really a combination of two things.
Two things.
Yeah, reaction distance and braking distance.
Okay, I'm not sure I follow.
So reaction distance is how far your car travels while you're reacting. You see something, you realize, oh, gotta brake. That takes time.
Because even fast reflexes, they're not instant.
Right. Your brain's got to process stuff, tell your body to move your foot to the brake pedal.
Takes a split second.
Exactly. And then you have braking distance. That's the distance your car travels while the brakes are actually on.
Okay.
That depends on a bunch of stuff. How good your brakes are, the road surface, how fast you're going to begin with.
So the faster you're going, the longer it takes to stop. That seems pretty obvious.
It is obvious, but those equations can actually tell you exactly how much longer. And it's not a simple relationship. Like, if you double your speed, your braking distance increases by 4 times.
Seriously. So going a little bit faster can make a huge difference in how long it takes to stop.
Huge difference. Something to think about when you're behind the wheel And that's just one way understanding motion helps us be safer drivers. But it goes way beyond that. This stuff applies to so many things. Playing sports, building roller coasters, launching rockets.
We rely on it without even thinking about it.
We do. It's like physics is the secret language of the universe.
And once you know a bit of the language, you start to see it everywhere.
That's a great way to put it. That's what I love about physics. It's not just about equations and theories. It's about understanding how the world actually works, from tiny atoms to giant galaxies.
So the same physics explains how a ball rolls down a hill and how planets orbit stars.
The scale's different, but the ideas, the principles, they're the same.
Pretty amazing. Well, we've covered a lot of ground today, starting with the basics of motion, all the way to some pretty complex stuff. What I'm taking away is even those complex ideas, you can break them down, understand them, if you put in the time.
Absolutely. And we've only just scratched the surface. There's a whole universe of motion and forces out there.
So much to learn.
So keep thinking, keep asking questions, and most importantly, keep exploring.
Couldn't agree more. Thanks for joining us for this deep dive into the world of motion. Until next time, stay curious.